students. We're back after a short period of time there, and we are going to be continuing where we left off last time. If you remember, I gave you some key points to recall in terms of organic chemistry, and here they are. In organic chemistry, it's all about carbon bonding, and carbon bonds very readily. They form covalent bonds, and please don't forget that carbon has 4 valence electrons. And we all remember what valence electrons are, right? Those electrons found in the outermost energy level. And covalent bonds are those formed when electrons are shared with one another. All right now, let's turn the lights back on. Let's get to where we're picking up here today, which are the types of carbon bonds. Yes, they are covalent bonds. We know that. But in organic chemistry, these covalent carbon bonds form in a variety of ways. And that's what we're going to focus on here right now. Think of baseball when you think of carbon bonds. In fact, I'm going to show you a little model here. This is a baseball player, and it's holding I'm using my imagination here. I'm using my imagination, but imagine this is a baseball player. Here's the bat. Here's the bat. Swing, bada, 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 swing, woo, home run. Now, why am I showing you this? Well, there's a few different types of bonds here on this particular model, and we're going to be using models to help us. But let's not hit a home run yet, okay? Let's stick with a single. This is an example of a single bond. Well, what does a single bond mean? I'll use this bigger model here to illustrate it for a moment. A single bond is one in which, and hopefully you can see this if I move off to the side, a single bond is one in which we have a single covalent bond between 2 carbon atoms. Now, I'm pointing to this model as if you understand what in the world I'm talking about here with the model. I'm going to show you a simple model here made with this black sphere in the middle. We're going to pretend for a moment that the black sphere is a carbon atom. So here we have a single carbon atom, and you'll notice there are 4 sticks coming out from this carbon atom. Well, what do they represent? Well, each of these rods represent what's called a covalent bond. And as you know, a covalent bond is one in which the electrons are shared. So think of there being an electron here, an electron here. These 4 rods illustrate that there are 4 valence electrons around this carbon, and they are being shared with valence electrons from other atoms. And in this model, the other atom happens to be a hydrogen atom. But when we talk about single bonds, we're simply referring to the bonds that exist, or how many rods or lines exist between 2 carbon atoms. So there's only one covalent bond here between these 2 carbon atoms. This is an example of a single bond. Well, how does that contrast with double bonds? Well, look at this model. If you look at this 3-dimensional model here, you can see that between these 2 carbon atoms, there's not 1 rod, there are 2 rods. And each of these rods represent a covalent bond. So between this carbon and this carbon, there are 2 bonds. So we call that a double bond. And I'm sure you can probably imagine the third one, if we hit a triple, here we have an example of a triple bond. There are 3 rods that connect our 2 carbon atoms with one another. As I turn this around, you can see there are 3 covalent bonds. This would be an example of a triple bond. So here's a triple bond. Here is a double bond. And here is a single bond. Very important that you get these three types of bonds straight. And I'm just going to show you another example of models because we're going to be playing around with these models as well. These have white rods to represent the bonds, black spheres for the carbon, and the white objects for the hydrogen. But right now, we're just looking at the bonds. You tell me, this will be a little quiz, even though it's a new model. What type of a bond, single, double, or triple, is this illustrating? Shout it out. Single bond, good. What about this model? What is this model illustrating? Call it out. Double bond, very good. And finally, this one, call it out. Good, triple bond. So you see how that works. All right, so far so good. We're off to hitting a home run in no time flat. Now, we deal a lot with models in organic chemistry, but it's really difficult to draw a model on a flat piece of paper. So there are different types of ways to write things, different formulas. We are familiar with a certain type of formula in organic chemistry. We'll talk more about that in a little while. But let me introduce you to different ways of writing things down on a flat piece of paper. So let's begin with this. There's what's called a structural formula and an electron dot formula or a Lewis dot formula. And this is how we illustrate on paper a single bond. Remember what a single bond looks like? And I'm showing you the different models to represent. And if you hold a model, and models can be extremely helpful in organic chemistry, because if you hold a model in just the right orientation, if you look at it just right, you can make out, there we go, you can make out what we call the structural formula. The black spheres represent the carbon atoms. Notice as you're writing down in your book, the two C's for the structural formula, those carbon atoms are connected with lines. And it's these covalent bonds that we're representing with the lines in this model. And on paper, you're representing them with straight lines. So all of these straight lines in a structural formula represent covalent bonds. And this is a really, really important point. I know I made it last time, but I'm going to ask you a question and answer the question immediately as loud as you can. How many valence electrons does carbon have, everybody? I hope you yelled out 4. 4 is incredibly important in organic chemistry. You may recall when we studied inorganic chemistry last marking period how like 8 was the magic number. Complete or filled outer energy levels. 8, magic number. In organic chemistry, the magic number is 4 because we're dealing with carbon. And I want you to look at something. Since carbon has 4 valence electrons, and incidentally, that's illustrated in the electron dot, the Lewis dot formation here. You can see that this carbon has 1, 2, 3, 4 dots around it. This carbon has 1, 2, 3, 4 dots around it. Those dots represent valence electrons, and it's only those valence electrons that form the covalent bonds illustrated in the structural formula here. So every C, every symbol C that you write down in organic chemistry must have and only have 4 lines coming out from it, representing 4 covalent bonds. So 1, 2, 3, 4. Do you see that? 4 is the magic number. Check out this carbon here. 1, 2, 3, 4. Get in the habit this week of counting the lines coming out from every individual carbon atom. You can't have less than 4. You can't have more than 4. You must have 4 and 4 alone, because 4 is the number of covalent bonds that form from 4 valence electrons. So what's the magic number in organic chemistry, everybody? 4. Let's go on to the next illustration here. Double bonds. Double bonds, again, if you remember the model, double bonds represented by 2 bars, double bond represented by 2 rods here. Well, double bonds on paper look like, well, this model drawn in only 2 dimensions. Notice the black spheres represent the carbon atoms. So on our structural formula, we've got 2 C's, each C representing a carbon atom. And out from each carbon, how many bonds are there, everybody? 4, the magic number. Check it out. This carbon here, 1, 2, 3, 4. This carbon, 1, 2, 3, 4. 4 is the magic number. How do we illustrate that on paper? This is the way we do it. Carbon, carbon, and a double bond is simply 2 lines. Remember, how many lines have to come out of every carbon? 4. So check it out. This carbon has 1, 2. We have to add 2 more. 3, 4. Now go over to this carbon. We already have these 2 lines, covalent bonds, coming out from it. How many more covalent bonds do we need? 3, 4. See how that works? In the electron dot configuration or formation or formula here, every carbon's got 1, 2, 3, 4. This carbon has 1, 2, 3, 4. Every carbon has 4 valence electrons and can form 4 covalent bonds. Hopefully you're catching on to this, and the next illustration should make sense to you. Here's a triple bond. Remember in our models, we've got, I'll hold this closer so you can see it a little bit better. We've got the 3 rods connecting the 2 carbons. We've got the 3 rods connecting the 2 carbons. And so in our 2-dimensional formula on paper, we can look at this model to help you draw it. But we've got our 2 carbons represented by the letters C. We've got the 3 lines, the triple bond between those 2 carbons. And then every carbon has how many lines, how many bonds, how many valence electrons, everybody? 4. So check it out on paper. This carbon here, we've got the triple bond, that's 3 lines. How many more do you need? 1. This carbon here, we've got the 3 carbons, 3 covalent bonds because of the 3 valence electrons. How many more do we need? 1. And if you look at that structural formula and we look at a model, do you see the similarity between them? I hope you do. We got carbon, carbon, 3 lines, 1 line, 1 line, and our hydrogens on the outside of those lines. And likewise with our valence electrons. So hopefully you can see that our type of bonds there can be illustrated two-dimensionally, given our starting point. So we're going to take this a little bit further here today, and I'm going to show you this picture here, and you'll see here are some condensed structural formulas. Hopefully this is starting to make a little bit more sense. Maybe not these yet, but hopefully this makes a little bit more sense to you. let's continue on. Because as again, we talk about different organic formulas, I want to make a distinction here for you. And the distinction is between what we have been using all last unit and what we're starting to learn about here today. What you have been used to all along are called molecular formulas. Important point here. Molecular formulas show the kind and the number of elements. If I were to write for you the molecular formula CH4, this looks totally familiar to you, I know. And you could tell me how many carbon atoms there are, everybody? 1. And how many hydrogen atoms there are? 4. In fact, I'm going to build for you a model of this molecular formula to show you with the next slide. Because all a molecular formula shows you is the kind of elements, and in this case, carbon and hydrogen, and the number of elements, 1 and 4. This is what you're used to. But in organic chemistry, since there are more than 16 million different kinds of compounds, a molecular formula isn't enough. And we're going to discover why that is this week. That's why we have to introduce the next type of formula to you, which is a structural formula. And I've already been making reference to structural formulas in your notes here. You've drawn a few of them down already, but let me show you the difference between the formula you're accustomed to and the structural formula. Unlike the molecular formula, a structural formula shows you not only the kind and the number, but it also shows you the arrangement of elements. In other words, it shows you where those elements are. It takes it a step further. It shows you what elements and how many there are, but it also shows you how it's built. Think about building a model of something, a car model, or building a bookcase, or who knows what, building something. It comes with instructions, right? Well, those instructions typically will give you a materials list and a schematic diagram of how to put it together. That materials list is like the molecular formula. It just shows you the parts that make it up. But the diagrams in those instructions are the structural formula. It shows you how it's put together. So with this structural formula, you can see that there's a carbon atom and there are 4 hydrogen atoms, just like that molecular formula before. But this type of formula, the structural formula, shows you how it's built. And I'll try and illustrate that with this 3-dimensional model of this particular substance. So if I hold it at just the right angle and you look at it, notice how the carbon in the center is that black sphere. We've got the 4 lines coming out from the carbon atom attached to hydrogen atoms, in this case represented by the red spheres. And notice the similarity in shape. We can see the arrangement of the elements with this 3D model as we illustrate it with the structural formula on paper. Here's another model that if I hold it in just the right orientation, you have to kind of twist it here, and I'm trying to do it in reverse for the camera and your benefit. It's much easier in person, by the way. But if I hold this closer to the camera, look at it again. How many carbon atoms are there, everybody? 1. How many hydrogen atoms, and in this case represented by the white pegs? There's 4. Notice the similarity between the carbon and the hydrogen in the model and the structural formula. Do you see the similarities? Hopefully you do. Because seeing things three-dimensionally and representing them two-dimensionally on paper is going to be really key moving forward, especially with tomorrow and the lab activity. So we're going to pause this now for now as we digest some of this information we just went over. Give you some time to review your notes for today as we prepare to finish up our notes next time we see each other. And so until the next time we meet, bye bye.